In this video, we will be looking at 13.1 Anova one-way analysis of variance, where we're going to be comparing three or more means. We did see in chapter 11 where we compared two means. Now we're going to be doing three or more means. ANOVA is very tedious to do by hand, but this video is going to show you an example by hand first. Examples of data and characteristics, we could be looking at children affected by exposure to lead. So low levels of lead in the blood could be one category. We have medium levels of blood and high levels of blood. So our characteristic that we would be testing would be mean IQ score in each category. So ANOVA is used when we compare three or more means. Okay. This is the test of equality for three or more population means. Our null hypothesis is always going to be that all the three means are equal. Alternative hypothesis would be always that at least one mean is different. At least one is different from the others. Null is all of them are equal. This is always going to be our null and alternative hypothesis. Here are the requirements for performing an ANOVA test. The populations have distributions that are approximately normal, or we should have large samples. Populations have the same variances, the standard deviations and the variances are same. The samples are simple random samples of quantitative data, and the samples are independent of each other. The different samples are from populations that are characterized in only one way. So in this video, I'm now focused on the calculator. I'm going to show you a manual example, but then I will also show you how to perform this using StatCrunch. So our goal would be to reject the null if p-value is less than or equal to alpha. If p-value is low, the null must go. And we would fail to reject the null if p-value is greater than the significance level. Okay. To calculate the f, our textbook does not have the f table, but I will be showing you, just like we saw the z table, t table, chi-square table, there's another table called f table, which gives us the critical values for ANOVA test statistic. F is the test statistic we would be using. It's variance between the samples divided by variance within the samples. Okay. So this is the ANOVA table that we will be using. For ANOVA table, we do need SS stands for sum of squares, DF stands for degrees of freedom, MS stands for mean squares, and this is the F ratio. Okay, so we need the source of variance here, or source of variation here, between groups and within groups. And then we have the totals column. To find the sum of squares between groups, this is the formula used. To find sum of squares within groups, this is the formula used. To find degrees of freedom between groups, the number of levels minus 1. So between groups, it's number of levels minus 1. To find the degrees of freedom within groups, it's the first sample minus 1 plus the second number in the sample minus 1 plus the size of the third sample minus 1. Okay, these are the sample sizes in each level. Mean square between groups is calculated by sum of squares between groups over degrees of freedom between groups. So to calculate the mean square, we would have to do sum of squares divided by degrees of freedom. Same thing here, sum of squares within groups divided by degrees of freedom within groups. Okay, that's how we find the mean square within group. Once we have the mean square between group and mean square within group, we calculate the F ratio. This is our test statistic. Okay, test statistic F ratio, which is mean square within group divided by mean square between group divided by mean square within group. And then we get the critical values from the F table using both degrees of freedom. There are different F tables for each level of significance. So if the level of significance is not given in the problem, we would go with alpha equals 0.05. In the supplement, I do have an example worked out for you guys. So we're given aspirin, Tylenol, placebo were tested to see how much pain relief each provides. So our null is that they all provide the same pain relief. This is like on a pain relief scale. After taking the medication, how much pain were people feeling. And null is all the means are same. Alternative is at least one mean is different. At least one drug provides better pain relief. So our summary, we have, this is the data given to me. And now we're going to do sum of squares, degrees of freedom, mean square, F ratio, and p-value. So to calculate the sum of squares, this is a lot of work, and we would be using this formula listed here. To calculate sum of squares within groups, we will be using this formula. So this number was found, the number 8 was found by using those formulas, and the 10 was found using the sum of squares formulas. Degrees of freedom is number of levels minus 1 between groups. So number of levels, we have 3 different levels. So it would be 1, 2, 3 levels. So that's why degrees of freedom between groups is 2. It is 3 minus 1. Within groups is number of elements in each sample. So within groups we saw sample size 1, 2, 3, 4. So it would be for within groups 4 minus 1 plus 4 minus 1 plus 4 minus 1, which turns out to be 9. And then to find the mean squares we just saw, we have to do sum of squares divided by the degrees of freedom. To find mean square between group, we would do, this would be 8 divided by 2, that gives us 4, and this would be 10 divided by 9, which is 1.111. And at the end, we calculate the F-test statistic by, we'll calculate the F-test statistic by using the formula F would be mean square between divided by mean square within. Okay, and then we do get the test critical values from the table. P-value can be calculated using a software like StatCrunch or a calculator. And then we make a decision whether to reject the null or fail to reject the null. Okay, in this case, we would fail to reject the null because my p-value is higher than the alpha in this case. And we did use alpha as 0.05. Okay. All right, so next example, here's the one that I want to work on with you guys. I did most of it, but you don't have this example on the supplement, but I did go ahead and write it down on page number 296. So is relief provided by antidepressants the same? So we have some data given, which is the some scale of depression people feeling after antidepressant medication was taken. So we are going to be given this data, this data, this data. The first group is our control group. The second group is our Praxil, people who took Praxil. The third one is Prozac. And we're trying to see if they provide the equal amount of relief from the depression. Again, keep in mind our null would be that all 3 means are same. They provide the equal relief. Alternative would be either one is different, okay? Either one of the means is different. All right, so let's go ahead and look at, this is the table we're going to come up with. Variance source, sum of squares, degrees of freedom, mean squares, F ratio. And we have between groups here and within groups, okay? So SS stands for sum of squares, degrees of freedom, mean squares. F ratio is calculated by doing mean square between divided by mean square within. So sum of squares between groups, we saw this is the formula to calculate sum of squares between groups. And we're going to use summation x1 squared. And I do have the x1s here. x1 squared is here. So I found all the sums here. Plug them at the right spots in the formula. And we get sum of squares between groups is this. The next, we're going to look for sum of squares within groups. The formula is slightly different, so we plug in all the values again from the previous table by using the sums from the bottom. And we figure out the sum of squares within groups is this. We also need degrees of freedom. Degrees of freedom between groups is number of levels minus 1. So that would be, we have 3 levels, placebo group, Prozac, and Praxil. So that would be 3 minus 1, which is 2. Degrees of freedom within groups would be sample size 1 minus 1 plus sample size 2 minus 1 plus sample size 3 minus 1. We had 8 people in each sample. We could have different numbers, and that's okay. In this case, all of them are 8. So 8 minus 1 plus 8 minus 1 plus 8 minus 1 turns out to be 21 degrees of freedom. Mean squares. To find the mean squares, we have to do mean squares are sum of squares divided by degrees of freedom. So to find the mean square between groups, I would be doing 46.083 divided by 2. And that's how I find 23.042. So mean square is sum of squares divided by degrees of freedom, whether you're doing between groups or you're doing within groups. Now, mean square within groups, I would have to do 97.25 divided by 21, which is 4.631. Once we have our mean squares, we're going to find the F ratio, which is mean squares between divided by mean squares. F ratio is calculated by mean square between divided by mean square within. Okay, so mean square between divided by mean square within, that is mean square between is 23.042. Mean square within is 4.631. And that turns out to be 4.976. Now that's my F test statistic. This is my test statistic, F test statistic. Let's look for the critical values from the F table. So I'm going to take you to the F table. Alpha is 0.05. We do need degrees of freedom for the F table. Okay, alpha is 0.05. So let's look at the F table here. F table, F distribution. Okay, so alpha is 0.05. We want to look at the correct F table. There's 1 for each level of significance. So we want to look in our degrees of freedom were 2 and 21. So I'm going to look down to here, and 21 looks like 3.4646, looks like 3 point. So in the column of 2 and the row of 21, I have 3.4668. Okay, 3.4668. All right, so let's go back and compare. So we have 3.4668 is my critical value, and we can see the test statistic does fall in the rejection region. So clearly test statistic does fall in the rejection region, and we're going to say reject H naught. So we can say at least one medication provides a better relief. Sufficient evidence to prove. There is sufficient evidence to suggest. We reject the null. When we reject the null, we have sufficient evidence. Sufficient evidence to suggest that at least one medication provides better relief. One med provides, either the sugar pill or the Prazil or Prozac provides better relief. Next, I'm going to play a YouTube video for how to do Anova using StatCrunch, because by hand it's very, very tedious. As you've seen, there's long formulas involved and it takes some time. So I'm going to play a YouTube video on how to perform Anova using StatCrunch. All right, here we go. One-way Anova using StatCrunch. Okay. All right, here we go. Okay, I'm going to make it a slide.
The National University. In this short video... Hello, this is Dr. Michael Myers, Associate Professor of Health Sciences at National University. In this short video presentation, I'm going to show you how to do a one-way analysis of variance, or an Anova, in StatCrunch. In our previous examples in this video series, we've been talking about analyzing data with the t-test using a one sample, so we have means from one group, two sample, having means from two groups, and now we're going to look at three groups. So when we have three means to compare, we use an Anova. In my class, I use a simple example of three groups of men. The independent variable here is their marriage status, a nominal level or categorical variable, married, single, or divorced, And you see here their happiness scores on a happiness test from 0 to 50, 50 being the happiest. So the question here is, are married men happier than single men or divorced men? What we want to do is compare the means of all three groups. This we do in an Anova in another distribution called the F distribution. Our null hypothesis here is going to be that mu1 equals mu2 equals mu3. The means of each group should be equal if nothing's going on. That's our null hypothesis. Our alternative hypothesis is that the means are unequal, that somehow the happiness is different in these groups. To do this in StatCrunch, all we need to do is get the data loaded in. Here I've typed it in, but you can pause this program and type these values in. Again, in StatCrunch, each row, when we do raw data, we want each row to be a subject. So you can see the first subject or patient, their independent variable is here, so the group they were in, whether they were married, single, or divorced, and their happiness score. So for example, the first subject was married and had a happiness score of 42. Unlike in our two sample tests in StatCrunch, we can easily do an analysis on this data without splitting the data. Here we're going to do a one-way ANOVA because we have one independent variable, marriage status in this case. To do the ANOVA in StatCrunch, we simply click on the Stat tab, ANOVA, one way. That will call up our dialog box and will tell the software what to do. If we had put that data into separate columns, we would click up here, but since we have the values in a single column, we're going to click here, values in a single column. We're going to look at our responses in the score, and actually here StatCrunch is smart enough to figure out which is the ratio or interval level variable, the numbers that are there. It's going to select just score. It's going to factor in the independent variable or the status. What we're going to do here is just do the simple ANOVA, so we'll just click compute. StatCrunch then prints out all of the stats for us. It gives us the number in each group, which is 10. It calculates the mean, the standard deviation, and the standard error. The first line here is the degrees of freedom between the groups. So there's three groups. That's going to be n minus 1, or 3 minus 1, which is 2. The next line is going to be the degrees of freedom within, which is going to be the total number in our study, which is 30, minus the number of groups, which is 3, so we get a degrees of freedom of 27. It calculates the F statistic for us and the p-value. So from here you can see in our happiness example we have a very large p-value, 0.88, which is way above 0.05. And again, this is the probability of seeing this value of test statistic or higher in our sample test. Here we have a very small F statistic, which corresponds again to our non-significant value. If we go to our table, we can compare this F statistic to our critical value in the table, just as we've done for our other tests. Looking at the F table, again, here's the degrees of freedom between the groups, so that's going to be 2. So we go down the 2 column, the degrees of freedom within is going to be our 27. So we scroll down, again this is the 0.05 table, so we go down the 2, get our 27, and our critical value here will be 3.35. So again, our F statistic here of 0.121 is not greater than our critical value of 3.35, further giving evidence that here we have a non-significant result. Your marriage status seems to have no bearing on your happiness in this sample. Once we're done, we can drag over and copy this data to put into our assignment or final documents. This is a quick demonstration of how we can use some sample data and perform a one-way ANOVA in StatCrunch.